My name's Alice Leach. I'm a Research Assistant Professor at the Vanderbilt Institute of Nanoscale Science and Engineering, or VINSE. Welcome to the Print Studio. Today, we're going to talk about 3D printing. 3D printing is a manufacturing technique that allows you to make a physical object from a three-dimensional digital model. This is typically by laying down many thin layers of a material in succession. There are a lot of different kinds of 3D printers: fused deposition modeling, stereolithography apparatus, selective laser sintering, and material jetting, to name but a few. The one you select depends on the materials you wish to print with, the size, geometry, and resolution of the object you wish to print, and the cost or time limitations associated with your print. In this video, we're going to focus on FDM and SLA printing, as these are the technologies available at VINSE. Fused deposition modeling, also known as fused filament fabrication, prints using a process called material extrusion. A spool of filament of solid thermoplastic material is loaded into the 3D printer. Thermoplastic materials soften on heating and harden on cooling, so when the filament is pushed by a motor through a heated nozzle, it melts. The printer's extrusion head then moves along specific coordinates, depositing the 3D printing material on a build platform, where the printer filament cools and solidifies, forming a solid object. Once the layer is finished, the printer puts down another layer, then repeats the process until the object is complete. Depending on the object's complexity and geometry, support structures can be added. For example, if the object has steep overhanging parts. Material extrusion printers are the most inexpensive and widely available form of 3D printer. At VINSE, we have two Prusa i3 MK3S FDM printers. Prusa printers are manufactured by the Czech company Prusa Research and are part of the RepRap project. The RepRap project started at the University of Bath in 2005. It's an initiative to develop a low-cost 3D printer that can print most of its own components. As Prusa printers are open source, the printer is easy to build and modify. It's also capable of printing with a wide range of filaments. There have been many variants produced by companies and individuals worldwide, and of course, the Prusa i3 is capable of printing some of its own parts. Prusa Research has an impeccable reputation, and the i3 MK3S has been at the top of 3D printer rankings since its release in 2019. While the original i3 MK3S is only capable of printing with one filament at a time, one of our printers is outfitted with a multi-material unit, the MMU2S, which allows the use of up to 5 different filaments in a single print. So let's break down the anatomy of the printer. We have filament up top to print with and a build plate or bed at the bottom to print on. There's a fixed frame and motors for movement in the X, Y, and Z directions, and an extruder, or write head, to heat the material and push it through the nozzle. The brain of the printer is the processing unit. The parts are powered by the power supply unit, and the user can interface with the printer through the LCD display up front. Most FDM printers have similar components, but there are a million ways that they can be connected together to produce a part. So, an FDM printer heats up a filament, pushes it through a nozzle, and then moves the nozzle along specific coordinates. Most common FDM printers achieve this by moving in Cartesian directions, X, Y, and Z. This movement can be accomplished by moving the extruder itself in all directions, systems known as delta bots, moving the extruder in X and Y while the bed moves in Z, known as fixed bed printing, or moving the extruder in X and Z while the bed moves in Y, known as moving bed printing. The Prusa is a moving bed printer. There are advantages and disadvantages to each style, but the moving bed style tends to be easy to maintain and modify, though it does put limits on the size of the bed and can lead to Z-axis print wobbles known as ringing. The Prusa has a bed or Y motor housed at the bottom of the tool, 2 Z-axis motors housed on the frame, and a moving X-axis motor. The position of the components on each motor axis are calibrated before each print by moving the part to its end stop or 0 point. Perhaps the most important and complex part of the tool is the extruder assembly. In the i3 MK3S, this part is responsible for heating the filament to the correct temperature, pushing it through the nozzle, and calibrating the position of the nozzle with respect to the bed. Heating is achieved using the appropriately named hot end. It has 4 component parts: the nozzle, the heat block, the heat break, and the heat sink. A thermistor and heater cartridge are nestled inside the heat block, which transfer the heat to the nozzle to melt the plastic. The heat break feeds the plastic into the nozzle. However, as it is in contact with the nozzle and heat block, it also heats up. If the heat break gets too hot at the top, the plastic, which expands when it melts, can overflow and disrupt the passage of the filament through the hot end. Because of this, the heat sink is added to the heat break. It has a large surface area to help transfer the heat away from the heat break. However, even that is often not enough, so most printers, including the Prusa, also have a dedicated heat sink fan to help the cooling process. The Prusa also has a cooling fan directed just below the nozzle to enable rapid cooling of the printed part. The top half of the extruder houses a motor and filament sensor. The gear of the motor grips the filament and pushes it into the hot end. The speed of this motor can be adjusted depending on the filament properties and required print speed. I also printed a visualizer for the motor, so I can verify it is turning correctly during printing. The tension on the gears can also be adjusted, with more flexible filaments requiring less tension in the gears to prevent entanglement. The filament sensor is an infrared sensor. It is constantly emitting a low-intensity beam of IR light. When the filament is inserted, a steel ball is pushed into the path of the beam, reflecting it back into the sensor, indicating an object is present. Perhaps the most important part of the extruder assembly is the Pinder Probe. This calculates the distance between the nozzle and the print bed. If the nozzle is too low, it can gouge the print bed and pull the printer apart, but too high, and the first layer of filament does not adhere to the bed correctly. Pinder stands for Prusa Induction Auto Leveling. It works the same way as a buried loop traffic light sensor, by sensing a change in the magnetic properties of the material in front of it. It's an air core inductor, and its inductance suddenly changes when the steel, with high magnetic permeability of the heat bed, gets close. Before printing, the Pinder Probe measures the inductance at 9 points across the bed to level the extruder with respect to the bed. This ensures a good first layer for every print. The last feature we should talk about is the heated bed. Heated beds are used to improve the adhesion of the filament to the build plate. They are also used to prevent warping. Warping occurs due to the contraction of the printed plastic as it cools. This contraction causes stress along the object's lateral surfaces. The quicker the cooling occurs, the greater the stress on the object. This stress is greatest at corners where 2 sides meet. There, the pulling stress exerted on both sides causes the corner of the object to deform and pull up and inward. Keeping the print warm helps slow this contraction and prevent warping. Typically, the temperature chosen is just below the glass transition temperature of the material. So, FDM printing uses a thermoplastic filament, heats it up until it's gooey, and pushes it through a nozzle. The nozzle then moves precisely in X, Y, and Z to define a layer. As the layer is printed on the bed, it cools and hardens. The next layer is then printed on top. This process is repeated until the part is complete. FDM printing is probably the most common form of 3D printing. It is also the least expensive, but it is limited in its resolution and tends to produce a rough surface finish. But what about other types of 3D printing? Well, next, we're going to talk about the i3 MK3S's cousin, the Prusa SL1, which VINSE uses for SLA printing. Stereolithographic apparatus, or SLA printers, use a light source to cure liquid resin into hardened plastic. The light source is usually a laser or projector, typically with UV wavelength. The resin is placed into a bath with the light source underneath. The build plate is lowered into the bath and the first layer exposed. The build plate then lifts up and the next layer is exposed. This process repeats until the object is complete. There are actually a lot of different kinds of SLA printer out there. Laser SLA printers use a laser beam to cure resin in the appropriate pattern, 1 pixel at a time. Dynamic light processing, or DLP printers, use a projector to cure an entire layer at once. At VINSE, we have a masked SLA or MSLA printer, the Prusa SL1. This works a bit like the DLP printer, but instead of projecting just the light required for each layer, an LCD screen masks unwanted light in each layer to create the appropriate image. So, let's break down the anatomy of the Prusa SL1. Well, in terms of movement, this printer is slightly different to the FDM printers as it only has 1 degree of freedom. That's Z. So you will see only one movement axis associated with the geometry of the print, and that's the Z-axis, also known as the tower. Attached to the Z-axis motor is the build plate upon which the part is cured. Down at the bottom, there's the resin tank. The base of the resin tank is made of transparent fluorinated ethylene polypropylene, or FEP film. This is a high-strength UV transparent and non-stick polymer, allowing safe storage of the resin, curing of the object through the film, and prevention of the object from sticking to the tank. Underneath the resin tank is the UV LED light source, reflector, and LCD screen. Also tucked underneath the tank are the electronics, the power supply unit and the control board. A fan and heat sink are in place to keep things cool, and a tilt motor is used to ensure the curing is successful. As each layer is cured, it sticks to the bottom of the resin tank. If this adhesion is not prevented, the part preferentially sticks to the tank over the build plate and turns into a single thin blob of cured resin. The tilt motor agitates the resin tank, pulling it down and pushing it up between the cure cycles for each layer. This pulls the part off the FEP film at the bottom of the tank and mixes the resin, ensuring a nice uniform part comes out the other side. An optical sensor is located at the bottom of the tilt arm to verify the tilt is complete. You may also notice that this printer has a cover, and it's a fetching orange color. While orange is one of Prusa's flagship colors, the color also prevents the UV-sensitive resin from the UV end of the ambient light in the spectrum, and our eyeballs from unwanted UV exposure should something go awry in the exposure process. You will also notice that this printer is housed inside a fume hood. The resin used for SLA printing is toxic, so not only do we work inside a fume hood when using this resin, but the printer also contains a filtration fan to absorb some of the fumes emanating from the printer while it works. As a final safety measure, the printer housing also contains a thermistor and lid interlock switch to prevent operation with the lid open and/or overheating of the tool. Next door to the Prusa SL1, we also have the CW1 curing and washing station. When a part's printed on the SL1, a tacky residue of uncured toxic resin is left on the part surface. This is removed by rinsing the part in isopropanol and then curing the whole part under a UV light source. The CW1 contains a stirring mechanism, tank for isopropanol, and a UV light source. The part is placed in the tank and rinsed, then cured under UV light. At that point, the part is cured and ready to go. When it comes to 3D printing, advances in tool design and construction have allowed exceptional print quality at the push of a button. However, in order to print a good part, it needs to be well designed and work within the limits of the printing technique chosen. For instance, the XY resolution of an FDM printer is limited by the size of its nozzle, which in our case is 0.4 millimeters. For an SLA printer, it is limited by the pixel or spot size of the light source. Typically, SLA printers can print details on the order of tens to hundreds of microns, while FDM printers are limited to the millimeter scale. Overhangs can be tricky to achieve on 3D printers without support structures, and long, thin features like spikes are challenging to print without stringing between features. The limits of 3D printers can be measured using a variety of test prints. Benchy the Boat and the Calibration Cat are some popular choices. However, at VINSE, we use the open source printer evaluation, developed by Kickstarter and Autodesk. It's an array of features like bridges, overhangs, and fine detailing, and they're printed in order to test for accuracy, resolution, and alignment. The Prusa i3 MK3S scores a 22.5 on this test, which is on the high end for RepRap printers. So, if you know the limits of the printer, you can design your part. But designing the object itself is probably the most challenging part of 3D printing. Computer-aided design, or CAD, is a key engineering skill in the 21st century. An abundance of CAD softwares exist, each with its own advantages and disadvantages when it comes to designing 3D printed parts. At VINSE, we use AutoCAD and Blender to produce .stl files. These can then be converted using a Prusa slicer to a .g-code file, which contains all the information required for the printer. Tutorials for both AutoCAD and Blender are available through VINSE. We also suggest consulting with a VINSE staff member or someone with 3D printing experience before you begin planning to determine the best design for your requirements. For more information on the VINSE 3D printers, check out our website at vu.edu/VINSE or contact vince@vanderbilt.edu. Thanks for listening.